HVAC 360 is brought to you today by coffee, making the job site a more alert place. Coffee is approved by safety officers everywhere who remind us to drink early, drink often, drink coffee. What's up? Welcome back. Matt Nelson here, your host for HVAC 360, helping you go further and faster in the field of HVAC. In these podcasts, I share stories, interview experts, and sprinkle some Miracle Grow onto your HVAC knowledge. Now, if you're new here or this leaves you wanting more, definitely go and subscribe to my list at HVAC360.com, and you will get instant access to additional golden nuggets of goodness that I serve up to you fresh on a weekly basis. Now, we're at episode number 82, where we answer the burning question, what is energy modeling and why can't I seem to get enough of it? All right, to answer these questions and more, we have for you today as our guest, Eric Kolderup, who, among many other things, is certainly a leader in the energy modeling field. Before we get into the interview, I'd like to state that a lot of engineers, design engineers out there, already are familiar with load calculations, but don't get them confused with energy models. Eric points out load calculations focus on design conditions, while annual energy simulations targets typical conditions. So in other words, load calculations are a mere snapshot of the most severe design day, while energy models take a look at the entire year. All right, please stick around afterwards after the interview, and I'll state my 3 favorite highlights from the conversation. So let's cut to the tape after a word from our sponsor. All right, today we're talking with Eric Kolderup, who is the principal at Kolderup Consulting, and also the current board of director president for the IBPSA USA chapter. So how are you doing today, Eric?
Very good. Thank you, Matt.
So I guess, what can you tell me about energy modeling? I mean, do you have anything about why is it so important?
Yeah, sure. So, I'm an energy modeler, and I've been doing it for, I don't know how many, over 20 years now. The energy modeling plays a couple of really important roles, and it could be in new construction or looking at existing building performance. But what I've found is that it's really important roles. It helps to integrate the results of the energy model, and the process of putting together an energy model integrates the impact of the decisions by the rest of the team. So there's the architect and mechanical and electrical engineers, and they all make decisions that affect energy performance of a building, right? And when you put together all the information about the design in an energy model, you see what the overall performance is. So it helps then, when you give feedback to them, helps everyone understand their role in building performance. It helps you identify the best path, you might say, to building performance. So I can help somebody decide where to invest their limited building capital. Should they put in better windows or better HVAC, a different kind of HVAC system? Should they put in more roof or wall insulation? So, through the process of doing this analysis with an energy model, we can help to optimize the building. And, depending on the climate, depending on the building type, the answers will be different in every case. So there's no one size fits all solution to building performance in my experience. For example, a number of years ago, I worked on a hospital new construction project. And when we did an energy model, it was in a mild climate. This was in San Francisco. But even in that mild climate, we showed that using heat recovery on the exhaust air could be a huge energy savings. And another big measure that the design engineers were trying to push for, but the owner was a little reluctant to look at, was using variable air volume to the patient rooms, which is many of your listeners probably know, hospitals would typically be done traditionally with constant air volume and very high minimum airflow rates for air quality purposes. But we could show that through energy modeling, if we went with VAV, and in this case it was dropping down to lower air changes at night when the codes would allow it, it was a huge savings. And in fact, the heat recovery and the VAV totaled up to something like over $500,000 a year in energy savings. And so it highlighted that the big issues in a hospital were the ventilation rates and the high air flow requirements. And then the model could be used to show that there were really significant savings available there. And they went ahead and implemented those measures. So there's a lot of cases where energy modeling, what I find in a lot of cases is that a design engineer, for example, has an intuitive sense of what the design should do. What's an efficient design for that application. But before they can really push the owner to make an investment in that, they need to do some quantification, and the energy model can provide the backup. So that's like one really important thing, is that it just provides us with some information about what we think we want to do. And then the other case is it surprises us. Energy modeling gives us insights into what is important. That might be especially important for somebody who's working on a project, maybe in a new climate they're not real familiar with. And in their own territory, they're used to, what makes sense and what's most efficient. But, this is maybe an obvious one, but it just recently also another hospital looking at it in Alaska. And my hospital's in California. We don't really care about the envelope at all because energy is so driven by the outdoor air ventilation rates and fan energy and so on. But clearly in Alaska, when you did the energy modeling, what do you know? The walls and the roof and all that, insulation levels do make a significant difference, especially the window performance. So those are just, I guess, a couple stories on, what makes energy modeling important. There a bunch of times, almost every project I do, whether it's office or retail, the energy model provides the rest of the design team with some understanding of where the building's likely to use energy and where the opportunities lie. And, it's almost every time, especially if they haven't been through a lot of projects where they've used energy modeling, there's kind of like a light that goes on. Oh my gosh, yeah. I thought that in San Francisco, I should be putting in R100 walls because somebody told me that that's efficient. But actually, we need to pay attention to our lighting energy because that's the biggest end use in an office in San Francisco. So it's an educational tool for helping to optimize buildings, I guess. That's one of the big important things.
Okay. Now, as far as the, on a per project basis, do you typically see energy modeling being used on all projects?
No, not yet. So, many projects are pursuing, say, LEED certification, green building ratings. Most of those projects do some energy modeling. In California, the energy code is pretty strict, although it's similar to the latest version of ASHRAE standard 90.1 in terms of stringency. But it, just like ASHRAE 90.1 does, it places an upper limit on window wall ratio if you want to follow the prescriptive method. So if in California, if you're over 40% window wall ratio, you do need to use the performance method for compliance. So that drives a number of projects that are doing energy modeling. And also utilities offer incentives for buildings exceeding the energy code, and that drives some too. I'd say, larger commercial projects, I don't have an exact number, but I'd say, at least half of them are using energy modeling, maybe more. Mm-hmm. And more design engineering firms have good energy modeling capabilities. And so more and more of them are using the simulation as part of their design in some way as well.
So I guess getting back to that, do you see yourself, are you strictly just an energy modeler, or do you do also some design work as well?
Yeah, I personally am only involved on the energy modeling side. So I guess my business is in a niche where I tend to work with some engineering firms, design engineering firms that don't have their own strong in-house capabilities, or have limited capabilities in-house, and they are being asked to do energy modeling by their architects or owners, and so I guess you'd say in a sense that I'm competing with the design firms that do in-house energy modeling, and when I started out 25 years ago, there were very few design firms that had good energy modeling capabilities. And so I was working with a firm that focused on energy consulting. And we would often be paid by a utility or a state agency to help the design team by doing some energy modeling and life cycle cost analysis. But over time, and appropriately, I think that energy modeling role has become more integrated into the design team. It's actually something that I sort of advocate strongly for. I actually did, 7 or 8 years ago at a national conference, I made a presentation on bringing building simulation into your office. And I'd done interviews with a number of firms, HVAC design firms, on how best to, or how they did energy modeling, and then presented some trade-offs. So some firms, they've got a group of a designated group. So they've got their designers, and then they've got their energy modelers, and they each sort of focus on those roles. Then there's another set of firms, a smaller group, but where they had their designers actually do their own energy modeling, and that was a really interesting case because they're great insights you could gain, sort of like I was talking about earlier, if you are modeling your own design. And it's a trade-off, right? Because getting up to speed on using energy modeling is a bit of a learning curve. But the benefits, I think, are really significant because you learn about the impact of various envelope components. You learn about the impact of lighting. You learn the importance of HVAC controls on energy use. So anyhow, that was a little bit of a digression there, but I think in spite of the fact that energy modeling's been around for a long time, we're still working out how to integrate it into our project teams in the best way.
So
that makes sense.
Yeah, no, and I think that it kind of at least to my mind, it has a couple different questions that bring up. Is energy modeling a very is it an art, or is it more of a science, or how where does it fall on that spectrum?
Yeah, good question, and that's one we talk about a lot. So I think it's definitely a science. The algorithms in the software are science, and most of them are well validated, meaning that if you give the right inputs, you get accurate outputs, that they match up well to actual building performance. And we understand pretty well where the uncertainties lie. But there's of course ongoing work happening in terms of developing algorithms and figuring out how to deal with uncertainty and all that. So in that sense, it's definitely a science. It's mature and well understood. But I think where the art lies is in using energy modeling, effectively and efficiently. I'd say, right now there are a limited number of people who who really have a deep understanding of the science, the software tools, and building systems. You kind of need all those three to be able to quickly and reliably get good results. So I think there's, so the science of it is pretty strong. The art of it is where, as an industry, I think we're kind of getting there. The tools are getting more robust and sort of easier to use, so they don't require the huge learning curve they once did. Hopefully we'll get to the point where the tools nudge us towards giving proper inputs. The art is that we're trying to avoid the garbage in, garbage out problem.
Mm-hmm.
And so that's where we are now. We're still not in a world where we can really easily translate the information from whatever it is, set of blueprints, or from an existing building into an energy model consistently and accurately. So that's where the art is, I think. But we could do that. The art is to do that without blowing the budget, essentially.
Right. So when you're, obviously with anything you have probably, good load calcs, good energy models, bad energy models. What are some things that keep you away from bad energy models? Is it more or less on the input side, or is it in interpreting the results, or where exactly does that lie?
Yeah, I think it mostly lies with the inputs. And there's a couple issues there. There's a limited time, in any project. If you're an energy modeler on a new construction project, you either have to get information from, say, the building owner and design team on, exactly when do you plan to get there in the morning and leave in the afternoon, or, how many computers do you anticipate bringing into this building? If the owner doesn't know that, or you don't have access to that information, then you make assumptions. And so, that's one of the that's one of the issues, one of the barriers to getting more accurate models. The other is just that there's you look at a set of plans. There's a lot of stuff there, and it takes a while for somebody to be able to understand what's there and get it into an energy model. So some people, have the experience to do that quickly. Others don't. So that's just another barrier to getting the input information in accurately. As people may have heard, there are a number of different workflows that are being developed. And sort of the holy grail that we've been pursuing in this industry for quite a while is getting from our BIMs, our building information models, in design tools, or 3D models from design tools, into an energy model, and to go back and forth. So as an architect, for example, develops a 3D model of their building, it can easily be ported over to an energy model and develop some performance information, and then go back and forth. And conceptually, kind of simple, but that's been the case for 10 years now, where I thought, okay, next year we're going to have this BIM to BIM workflow really, really worked out. But as people find, there's all these unexpected questions. There's stuff that's come up, like the BIM model has thicknesses of walls, because that's the actual building design. Most building energy models don't consider thicknesses of walls. They just kind of want to know where the wall is and what its thermal properties are, like its U value and heat capacity. And So when you go from one tool to the other, do you put the wall surface at the outside or the inside or in the middle? And there's all these little details that the industry is trying to work out and develop standards for. Anyway, the short story is that we will someday get to a world where there's a more robust way to translate this information between designers and models. There are also efforts looking at the other big thing that energy modelers struggle with is, I got this train package unit that's being proposed. What is the performance data for that thing? We need to know more than just the EER for it. We need to know, what its performance is over a wide range of outdoor air temperatures and airflows, and so that we can sort of create a performance map for that. So one manufacturer publishes some of that data, another doesn't, so you got to make assumptions. But, another tangent here, but there's a new ASHRAE standard under development. It's called Standard 205. And that group is working to create standard data formats for equipment performance. So if you have a package unit, for example, here's how each manufacturer, would report the power and capacity at a bunch of different conditions. And then those data in a standard format so that an energy software could read that in and, you could accurately model the impact of that system. That's a pretty exciting thing. I mean, it sounds like a pretty boring thing, but it's a pretty exciting thing from an energy modeler's perspective. They're also working on similar formats for, say, chiller performance, fan performance, so that we're overcoming some of that barrier to getting accurate information into the energy models, where now it's a little bit of an art to figure out how to represent a train unit or a carrier unit based on what information is available to you.
Right, because when you talk about the EERs or whatever the performance specifications, typically that's going to be kind of a snapshot of whatever the equipment is, so they can kind of select a best case scenario. But that's not the reality of how it's going to perform over a broad range of design, not design days necessarily, but actual days, so you have, shoulder days, summer days, winter days, how is it going to actually perform across all those different, conditions?
Yeah. And that's, I'm glad you brought that up. That's the whole point to doing an energy simulation. We could, as you noted, EER is a full load efficiency at, say 95 degree outdoor temperature. And that particular condition happens only a few hours a year. So if we want to compare two different HVAC systems, one may look better in terms of full load efficiency, but what does it do over the full year? And, when you do a simulation, you quickly learn that it's all about part load efficiency. And if you can get hourly outputs, for example, from a simulation program, and you could look at your chilled water plant load, for example, and you see that, okay, it reaches that 100% load 5 hours out of the year. So do we really care about that? It's sitting at its 20% load, 1,000 hours a year. And so that makes it real clear that we need a chiller that can unload efficiently. And so as long as we can get decent part load performance from those manufacturers, we can compare manufacturer A to manufacturer B and see what makes sense in this case. And that's, I've done that analysis for a couple projects, like some medical office buildings where they were replacing chillers, and they wanted to see, well, should I go with an air-cooled chiller or a water-cooled chiller? I've got a couple different air-cooled chillers, one that's got multiple compressors, one that's, screw versus scroll. And you can get, a decent amount of data from the manufacturer and do a simulation to see, for this building, given its load profile, in this climate, given the typical outdoor air temperatures, which is best. And that's a real powerful role for simulation.
Right, and it gives you a lot of different decision points to discuss with an architect. And I mean, obviously, you were talking about BIM earlier, and how essentially, I mean, I don't know, I have kind of the belief that architects really struggle with the actual performance of an envelope of the outside of a building, and they're mainly focused on the way it looks and the way it makes people feel, which obviously is important, but also the performance is important. And I think that getting that BIM type of mentality will not only help them make smarter decisions about windows and wall construction, but you're going to be able to, that's also going to impact how you select equipment, because obviously, unless you don't know, equipment comes in certain sizes. It doesn't come in, every size. So, by increasing the performance of a window system 5%, you might be able to kind of, cut your mechanical system by 20%, get it down to the next level, things like that.
Yeah, that's another great point. This is especially, there's a big push amongst a lot of people in this industry to do early energy modeling, like, at conceptual design phase, or even before that, before, the ideal case is before the owner and the architect have sat down with a cocktail napkin and kind of sketched out what they think the building should look like. You should do an energy model. You could there's one process called simple box modeling, right? So you don't even know what the building looks like. You just know, it's going to be in Chicago, and it needs to be 200,000 square feet. So, you create a simple model of a 200,000 square foot building in Chicago, and then you run a bunch of alternatives. You vary the window area, you vary the roof and wall insulation, window performance, and just you can do this in like an hour, and you can say, hey, for this type of building here, using typical assumptions, of course, these building forms are going to give you a lot lower loads, and your windows have about this much impact, et cetera, et cetera. And then, so they can inform their early design decisions. And then kind of what you were getting at a little bit further down the road, like in schematic design, where you're trying to decide, am I going to use window shading or not? Am I going to go with that, low transmission glass or not? Or, exactly how tall should the windows be? You can say, and I've seen this on a number of projects, in some cases even, well, if we go to like a triple pane low E window, of course we know that's going to be expensive, but we could do away with the baseboard heating system altogether if we do that, and save, X amount of energy. Or, as you were alluding to, you can cut the size of the chilled water plant if you go with the shading, for example. And so we can justify some of these envelope upgrades, which can have a significant impact, by doing simulation to show that we can save money elsewhere. Real powerful tool. And, it's kind of one way for the architect's decisions and engineers' decisions to be on the table together and figure out, the optimal path.
Right. And
so, that does happen sometimes. Doesn't happen in the standard project, but we're trying to get there.
So obviously, you've talked about, optimizing again. When you say that, it makes me think of net zero buildings. So, I mean, how does energy modeling and net zero buildings kind of, factor in? Yeah,
this is kind of a new frontier for the building industry in general, of course. The big deal with net zero energy buildings is it puts new demands on energy models. Up till now, before the net zero energy buildings rather, we were using energy models to compare alternatives. Do I go with option A or option B? Do I use this chiller or that chiller, or this window or that window? And what we were really interested in was the relative performance difference between the two. We weren't really trying to predict the actual energy use of the building. And it wasn't that important to do that. We just needed to know the relative difference. And modeling simulation is great for that. Now, the owner and the design team wants to know, how many photovoltaic panels do I put on the roof? And they're expensive. and so it's an important question. So you got to know, how many kilowatt hours of energy is this building going to use per year? And so now the energy model needs to reflect as accurately as possible all of the actual operation of the building. So before, whether, you didn't really care whether the system startup schedule went, 6 a.m. to 6 p.m. or 5 a.m. to 7 p.m. The relative performance of the two systems would still be, in the order, you'd still get a good answer about the relative performance of two systems. Now, if you get that schedule wrong, well, your kilowatt hours are going to be pretty far off. So what it means is that we have to spend more time on our energy models. We need more discussion with the future building occupants about, what's your operating schedule going to be? We have to talk about, how many computers they're going to bring in there. We need to talk about, are they going to turn the lights off during the day or not? Those kinds of things. But so that's a challenge, but it's also, a really big opportunity, because now we're also starting to get into what's really important, which is the absolute energy use of the building. And one of the things you find if you do an energy model is that plug loads are often a really big deal. And as we're making our envelopes more efficient and our HVAC systems more efficient, we're shrinking the pie, but that plug loads piece of the pie is staying the same. And so what I've seen in a lot of net zero projects now is that the owners are being brought to the table and say, okay, now you have a job as well. You have to think about the efficiency of your computers and your copier. If you've got a kitchen in there, we got to think about demand control ventilation on the hood. We got to think about all those things that design teams might not have been responsible for in the past. And so I've seen several cases where buildings were designed to be net zero, and then in operation, especially the first year, they don't get there. The energy model was under predicting the actual energy use for some reason. But then it's usually, in all the cases I've seen, it's a starting point for, the exploration of, well, have we commissioned these projects properly? Are they being operated differently than we thought? Is something wrong? And usually, it's that we find something's been improperly controlled or something got overridden, et cetera. So this is something that we should have been doing all along, even if it wasn't a net zero building, right? Net zero building, you see the utility meter and you say at the end of the year, did we add up to zero? You know whether you made it or not. And so if you didn't, you got something to compare to.
Right, because I mean, even that, obviously net zero is one goal, but even if you look at, say, ASHRAE's BEQ process for grading buildings, you have the as modeled, and then you have as operating. So you have kind of the two metrics, both on the same scale, and you can kind of see exactly, where they're lining up, and that you might have the case where you need to tweak a building until you get it operating the way you thought it was going to operate.
Yes, right. And so the ASHRAE BEQ, they've got the as designed, where you do energy modeling with some sort of standard operating assumptions. And then the as operated, which is how the building's actually being performed and used by its occupants. And so if you see a difference, then maybe the building's not being used properly. It sort of brings up the topic of the role of simulation in existing buildings. And this idea is that, well, kind of like with new buildings. So if we've created a model during the design phase, and then we see that the actual utility bills don't match up. So we go back, compare the model outputs to utility bills, and the utility bills are higher. This gives us something that we could use in the commissioning process or perhaps recommissioning process to say, well, why is it different? And it could be something, easily explained as, well, the weather was different this year compared to the typical year. But it also could mean that things are not being operated as expected. And I've had a couple of personal experiences where I created a model of an existing building. One was a big laboratory building. And I tried to calibrate the model, to get it to match up to measured data. In this case, we had measured data for chilled water and steam usage as well as electricity. And I just couldn't figure out how the building could be using the energy that it was using. It was using more heating than my model would predict. And at some point, I came to the conclusion, well, my model's right. This building is wrong. And so further investigation found that there were stuck valves in the heating system. So it was doing, it was heating up the air and then cooling it back down again. And so sometimes when we do these simulations, it can help us to figure out that something's wrong. And it won't always tell us exactly what's wrong, but it can kind of point us in the direction. We can go find stuck valves. We can find economizers that aren't operating properly. We could find, supplier control sequences that haven't been implemented, those kinds of things. So that simulation is also a powerful tool in an existing building to try to potentially identify problems.
So you are the current president of IBPSA. That is the International Building Performance Simulation Association for those that are keeping score at home. What can you tell me about IBPSA and what it does? What's its mission?
Sure. Well, I can tell you the acronym's a mouthful. That's a little bit unfortunate, but here's what it is. So IBPSA is actually an international organization. I am on the board of IBPSA USA, which is the U.S. affiliate. So there are affiliates in dozens of countries around the world. The IBPSA USA, we've got, the mission, actually our specific mission statement is fostering better building performance through simulation. The organization, we hold conferences. So every other year, we have a simulation conference. This year, it's in September in Chicago, coming up in 2018. For the last several years, we've been co-hosting these with ASHRAE. So it's a joint conference between ASHRAE and IBPSA USA. The members of the organization, we're a professional organization. The members are energy modelers, researchers, software developers, people who develop these simulation programs. University professors, policymakers, that there's been a pretty strong growing interest over the last 4 or 5 years. The demand for simulation has been growing, the interest in simulation has been growing, so the organization's been growing too. There's also training. This is also, we developed a training program. It's a one-day building energy modeling training that is also sort of jointly presented with ASHRAE. So it's as part of the ASHRAE Learning Institute. And there's going to be one session of that coming up in June at the ASHRAE conference in Houston. We've got chapters all over the country. We've got over a dozen chapters in cities around the country. And then what's exciting to me is over the last 2 years, we also had 2 student chapters start up, one at UC Berkeley and another at Stanford. So there's a growing student interest in this field. One thing I should say is that, the name is building performance simulation. So energy modeling is a big part of it, but it also includes people doing things like airflow modeling, computational fluid dynamics analysis, also daylight modeling. So at the IBPSA conferences, you've got people looking at beyond energy to doing airflow, light, some acoustics, all aspects of building performance. So, and then there's a bunch of committees. We've got some really active research committees. And one I think that's interesting to highlight is there's a sort of an architectural simulation subcommittee of research. And they've got a project going on now they call Project STASIO, STASIO. It stands for Standard Inputs and Outputs, or Standard Simulation Inputs and Outputs. So that's like a collaboration between modelers and architects, and they're trying to come up with some best practices on how to present modeling inputs and outputs to design teams so that people can understand them. I think it's come from stimulated by some frustrated architects who've had to work with nerdy energy modelers and try to understand what they're trying to say. So that Project Stasio is something that they've got a website up and a lot of interesting work going on. So anyway, so that's a little bit about IBPSA. So I think it's a good home for people who are interested in simulation and getting training, going to conferences, learning more about it.
Now, is there any sort of online components that match with this conference training that you do?
Yeah. Well, so through the ASHRAE Learning Institute, there are usually once or twice a year there's a sort of live online presentation of this. There are a number of videos that are available at the IBPSA website. It's IBPSA.us. You can find actually some snippets from that training. So, like 10-minute videos that go through some of the fundamentals of energy modeling. So that's something that people who are simulation curious can check out. Those are currently there free online.
All right.
So those are a couple things.
Good. I think that that pretty much covers it. Anything else that you'd like to mention in as the last word? I would just say that I think this is an interesting field. If you're sort of a young person, one of the things that really attracted me to energy modeling was getting the high-level system view of a building, how all the integrated parts work together from an energy performance point of view. So, if you're kind of a generalist. So, if that's appealing to you, then this is perhaps an interesting field to get involved with. And that there are, there are firms out there that focus on energy modeling. There are firms that, design firms that need energy modelers. So I think it's a growing dynamic field that someone could find rewarding. Excellent. All right. Well, I appreciate your time, Eric, and thanks for the interview.
Sure. Thanks, Matt. Bye.
All right. Thanks again to our guest, Eric Kolderup, for taking the time to chat with us. Check out the show notes for links and things that he mentioned during the interview. You can find those show notes at HVAC360.com/82. As promised, here are my 3 highlights from the interview. Highlight number 1, obviously the growing use of energy modeling. Right now you can use a rule of thumb if you're not using a prescriptive method or using window to wall ratio of 40%. That might tick you, like he said, to have to go to more of an energy model. But obviously we have net zero, we have high performing buildings. All of this is coming up in our future, and it's going to happen whether you like it or not. So you might as well get there first instead of trying to drag your heels and waiting for it to be mandated on you. So that's that. Highlight number 2, obviously bad information leads to bad modeling assumptions. This stresses the ability to communicate not only with the design team, but with the owner. Here's an idea for you that I thought of. Why don't you get that in writing, these design assumptions down, get them all in writing, get the owner to sign off on it. Even if you have a argument after the fact, at least it is a starting point to say, okay, here's what I understood at the beginning of the project, and here's what is happening now. So at least it gives you a basis of discussion for any issues that may arise in the future. All right, highlight number 3, learn to optimize the system selections using these energy models. Easy for me to say. Designing for part load optimization really is going to be key. I mean, it's a new skill that's out there, not just designing for peak load conditions. In other words, you really need to right size your HVAC equipment, even if it really requires you to increase the thermal performance of your envelope to be able to downsize to that right type of equipment, that right system. All right. Thanks everybody so much for listening. Hope this was helpful to you. If you know somebody involved in energy modeling or load calculations, why don't you share this episode with them? Use this as an opportunity to increase the value and increase the value of your connection with them, just as a common courtesy. Also, as mentioned in the top of the show, please subscribe if you haven't already to the list at HVAC360.com for more goodies and weekly updates. And if you're so moved to do more, consider leaving a review at iTunes. All right, well, that's it for this episode of HVAC 360, helping you go further, faster in the field of HVAC. So until next time, know what you build and share what you know.